Ben bir mühendisim. Ofiste, evde, yaşamın her alanındayım. Görülmeyen ama hissedilenim. Ben ne kadar görünmez olursam, projelerim o kadar başarıyla tasarlanmış ve uygulanmış demektir. Tıpkı sizi sizden fazla düşünen gizli bir kahraman gibi. Kahramanlık, kağıtla kalem bir araya geldiğinde geleceğe yön verebilecek kadar cesur olmaktır. Çünkü mühendislik, bilim ve doğa alanında tüm bilinenleri yine doğa ve insanlık için kullanmaktır. Tasarımda sadece estetiğin değil, sürdürülebilirlik, enerji verimliliği, çevre duyarlılığı gibi kavramların da altını çizmektir. Mühendislik, modern, konforlu ve doğaya saygı gösteren yenilikçi yaşam alanlarını hayal etmek ve gerçeğe dönüştürmektir. Gelecek kuşaklara yön vermektir. Binlerce yıl önce bir kıvılcımla yaratılan aydınlığı bugün tek bir tuşla milyonlarca insanın yaşadığı yerlere taşımaktır. Geceyi gündüze, soğuğu sıcağa, sıcağı soğuğa çevirebilmektir. İnsanlığın ihtiyaçlarını karşılamak için hayallerimizi gerçekleştirirken yanımızda TTMD vardı. 1992 yılında kurulduğundan bu yana çatısı altında güven bulduğumuz, etik değerlerin teşkili ve temel sorunların çözümü için birlikte çalıştığımız yol arkadaşımız. Farklı disiplinlerden gelen profesyonellerin ortak amaçlar için toplandığı TTMD, üyeler arasında iletişim ve tartışma ortamı yaratıyor, bilimsel ve teknolojik yayınlar yapıyor, üniversite, sanayi, işbirliğine destek veriyor, çevreci ve enerji verimli çözümlerin yaygınlaşmasını destekliyor, yurt dışındaki gelişmeleri izliyor ve sektörü yurt dışında temsil ediyor. Bizler tüm insanlığın iyi yaşam arayışına çözüm buluyoruz. Bizler yarınlarımızı şimdiden kuruyor ve daha sürdürülebilir bir dünya için çalışıyoruz. TTMD, 1992'den bugüne yaşam mekanlarında insanlığın konfor ihtiyaçlarını doğaya saygı göstererek sağlamak için var. Mühendislik mesleğini etik değerler doğrultusunda uygulamak için var. Türk Tesisat Mühendisleri Derneği, gelin geleceği birlikte yaratalım.
Doğru hava uzmanı.
PP bazlı 3 katmanlı yapısıyla ses yalıtımlı, yangına dayanıklı, üstelik halojen içermez. GF Hakan Plastik'ten GF Silente Extreme sessiz koruyucunuz.
Herkese iyi akşamlar diliyorum. IBIPSA Türkiye'nin yani Uluslararası Bina Performans Simülasyonları Birliği Türkiye ayağının ve TTMD'nin bir başka webinarında bugün birlikteyiz. Bu webinarımızda konuğumuz Dr. Drury Crawley. Ben birazdan kendisini tanıtacağım. Ben doçent doktor Gülsu Ulukavak Harputlugil, Çankaya Üniversitesi Mimarlık Bölümü öğretim üyesiyim. Aynı zamanda IBIPSA Türkiye'nin de başkanlığını yürütüyorum. Şimdi önce sizlere birkaç bilgilendirmem olacak. Ondan sonra da İngilizce sunumla ve bundan sonraki bölümünü webinarın İngilizce olarak devam edeceğiz. Ses, görüntü veya benzeri bir konuda herhangi bir teknik aksaklık yaşarsanız GoToWebinar içerisindeki chat kısmından lütfen teknik masamızla ulaşınız. Etkinlikten kopar veya tekrar katılma problemi yaşarsanız webinar@ttmd.org.tr adresine mesaj atabilirsiniz. Panelistlerimize sormak istediğiniz soruları GoToWebinar içerisindeki Questions kısmını kullanarak iletebilirsiniz. Sunumun sonunda soru cevap bölümüne yer verilecektir. Bu bölümde mümkünse sorularınızı İngilizce iletirseniz daha rahat hemen iletmem söz konusu olacaktır veya çevirmem gerekecektir Türkçe iletirseniz. Webinar sunumu TTMD üyeleri için TTMD portala yüklenmektedir. Tüm webinar videoları ise TTMD YouTube kanalında bulunmaktadır. Bu webinarda daha sonra orada bulabileceksiniz. Herkese iyi seyirler diliyorum. Good afternoon, ladies and gentlemen. My name is Gülsu Ulukavak Harputlugil. I'm an associate professor at Çankaya University Architecture. And besides, I'm a chair of IBIPSA Turkey affiliate. Today we are here for another webinar organized by IBIPSA Turkey, collaboration with and support of TTMD, Turkish Society of HVAC and Sanitary Engineers. Today our webinar guest is one of a special and famous name of building simulation world, Dr. Drury Crawley. Today, Dr. Crawley is going to talk about impacts of climate change and urbanization on future building performance. Thank you, Drew, for being here with us. Dear audiences, if you have questions, you will use the questions panel for that. At the end of the seminar, I will ask you your questions to Dr. Crawley. Now, first, I want to introduce Dr. Crawley briefly, and I'll leave the screen to Drew. Drew Crawley is a Bentley Fellow and Director, a building performance researcher focusing on building performance, zero energy buildings, decarbonization, digital twins, smart cities, sustainability, and resilience. With more than 40 years of experience in building energy efficiency, renewable energy, and sustainability, he has worked in engineering, software development, government research, and standards development organizations, as well as building design and consulting companies. He received his PH.D. in mechanical engineer from the University of Strathclyde in Glasgow, Scotland, on the topic of building simulation as a policy tool, and a Bachelor of Architecture from University of Tennessee, and is a registered architect. Dr. Crawley is active in ASHRAE, Director at Large at ASHRAE Board, member of Task Force on Building Decarbonization, Chair of Standard 169, Climatic Data for Building Design Standards, member of SSPC 189.1, Standards for Design of High Performance Green Buildings except Low-Rise Residential Buildings, as well as member of many standards. He's also active in the International Building Performance Simulation Association, IBIPSA Vice President since 2018, at large board member since 1998, fellow in 2012, regional affiliate Legion since 2006, and also he has several roles, IBIPSA USA. He was previously active in US Green Building Council, member of the American Institute of Architects, and affiliate member of CIPSE, and serves on the editorial boards of the 3 international journals. He has written more than 125 papers and articles, and lectures at more than 40 universities, and made more than 400 presentations on building energy efficiency, sustainability, and renewable energy throughout the world. And also he's an ASHRAE distinguished lecturer. He has given more than 180 presentations and workshops for more than 90 ASHRAE chapters throughout the world. I think it is enough true, but if you need to add more about yourself, please. Now the screen is yours. Thank you.
Thank you, Gülsu. No, I think that's more than enough introduction. Thank you very much. Okay, let's see. I'll get started here. And I do that first. Okay. Well, thank you again for inviting me to talk today. This has been one of my most popular topics recently, looking at climate change and urbanization. And I'm very glad that ABIPSA Turkey have expressed interest, and so I'm looking forward to to being able to share that with you today. So let's see, let's get started. So I always like to start my talks by talking about why we care about building energy use. Building energy use in general is responsible for most of the carbon that's released into the atmosphere. There are other sources, but it's a primary. And worldwide, buildings are a significant contributor to that. Buildings are about 30% of energy use worldwide. It varies quite a bit. You can see depending on where you are and which area and how the economies develop, it depends. So globally, industry is still about 50%, but in many places in Europe and North America, it's much less. If you go kind of to the middle to Europe, Greece, Lebanon, Middle East, you'll kind of get a feel for what I think Turkey is. I didn't have data on that, but you see that Europe in general is still about 35% industry, but buildings are now approaching 40%, and that's what you see in many countries. If you go back to the third and fourth bars, you'll see China and Hong Kong, kind of the two extremes. China, 70% still in industry, but buildings are now accounting for 20%. And if I took this chart back 20 years, that would have been closer to 10 or 15%. So buildings have become, as an economy develops, becomes less industrialized, more service oriented, you'll see the buildings take more. And you see that in the extreme of the fourth column, where Hong Kong, 65% is for buildings, very little industry, and transportation is still an important part of that. So that's what we see. And globally, if we go to the last bar, my next couple slides are about the US, because I have good detailed data there, but the US is about 40%. So it's kind of in that range where you see many places in Europe are today, that industry is still important, but buildings now are the largest contributor to energy use. So at 40%, about half for our homes and half for commercial, a little less for the non-residential sector. And in terms of energy use, it's important to understand that it's not just the typical things that you may think of your homes as having, or even 20, 30 years ago, heating, water heating, maybe cooling, refrigeration, and some excuse me, other appliances. But today we have many more things going on. We have more appliances going in, our televisions, even our computers are beginning to take more of a role there, even showing up on here is 1%. But I think the important thing to see on this chart is not just those individual ones, but the other uses. A full quarter of things going on in our homes, energy uses, are now small devices like our phones and all the other things that are connected to the internet that weren't there even 15 years ago. So a lot of energy use is going for that hasn't been there in the past. So if we're going to deal with residential energy use in particular, we have to deal with all of it, not just the top 2 or 3. Excuse me. In the commercial sector, the non-residential sector, kind of similar sort of thing, but there is no typical building. If I were looking at a supermarket, grocery store, refrigeration would be a full half of the energy use, followed by cooling and lighting. So it's definitely depends on the building type. If our offices, we're probably talking cooling, lighting, heating, ventilation is our top exercise. But again, there are a whole slew of other uses here, in this case 28%, showing what's going on, and it's beyond, it's not including the office equipment and computing. You see they're contributing to another 13% of the energy use now, so they're quite a large proportion of that. So if we're going to deal with decarbonizing, looking at carbon as an issue, we have to deal with all the aspects of how our buildings use energy. So on to the top, looking at climate change. Well, first, let's look at some definitions. They're not the same. Weather is what's happening now, what the wind speed is, where the wind's coming from, what the temperatures are, what the humidity is, cloudiness, pressure, etc. It's kind of an instantaneous snapshot of what's going on. Climate is a composite of that over a region, or maybe over a series of years. In fact, many times we talk about it's 2 degrees above normal, or it's very cold for this time of year. And that's based on a climate snapshot. And in many places, the meteorological world, they do a 30-year snapshot, what they call normals. So our latest set of normals would have been through 2020. And so we're comparing to that past 30 years to see what's going on. And we are seeing changes there, and you'll see some of that as I move forward. This is a snapshot from just before 6 in the morning to 6 in the evening, just one day at a research laboratory in Colorado. And what we're seeing here is kind of the variation. It's not static like we see. If you're used to working with weather data for building simulation, we're looking at hourly snapshots, and you can see here this is changing at a 5-minute increment, and that's more the measurement than anything else. So you see the green going across. We have cloud cover interrupting the greens being the solar. In this particular case, it's clouding up in the early afternoon. Possibility of rain. I don't believe it rained. The temperatures throughout the day are varying, both the dew point and the dry bulb temperature. Also, wind speed is changing here. And so it is not just a single snapshot of this, and we need to remember that if we're using a single point, that there's a lot going on in between those 2 points. Especially, most of the data we have is hourly. This is unusual that you have this sort of snapshot of this detail. So the New York Times has been publishing these really fantastic infographics that you can put in your city and see how much warmer. 2016 globally is still the warmest year on record. I put in Istanbul, but I could have put in any others. I looked at Ankara, and it was similar sorts of things. But what they show you is a normal range, and you see kind of a gray area behind the red bars there. And the gray area is kind of normal. And what you're seeing is that for much of 2016, from the winter, the spring, the summer, was much warmer in Turkey, particularly in Istanbul. In this case, the average temperature is supposed to be about 16.6, and that year was 3 degrees above that normal. So that quite a bit more change. At the bottom, it's a little harder to see, but total precipitation for the year was about 20% less than normal. So that can play into this as well. So this is one range of that. The second warmest year, they did similar sorts of things, and in this case, Istanbul was even warmer. It was a warmer year in 2019 than it was in 2016. And we'll see that vary. It's not, the global average doesn't mean it's always the same, but we're seeing consistently higher temperatures winter, spring, and summer throughout the year. So this gives you kind of a snapshot of what's going on globally. Several things here. You'll see lots of gray right now. That's because there's no data back in the 1800s. As we get to about 1880, we get more consistent, have data. On the right, you'll see a bar with a temperature anomaly. You go into the blues, it's getting colder. You go into the oranges and reds, it's getting warmer. At the bottom, you'll see kind of a global mean temperature. This is relative to what the IPCC uses as a baseline, 1951 to 1980. And you'll see that for much of early in the century and even back to 1850, globally, the temperatures were below that. You'll see it starting as we move into the 1970s and 1980s. Now we're moving into the reds and the oranges, and even in 1990s. Now we get some back and forth. You'll see some cold spots, hot spots globally, but consistently we're seeing that. So we're already, by the time 8 or so years ago, beginning to see temperatures above that range, in the range of a half a degree, and now as we get closer, the last 5 years and the hottest years on record, almost a full degree globally above that. So it is already visible that we are seeing a strong trend from, if you look at the beginning of the last century at 1900 through today, we're seeing almost a degree and a half temperature change that we can show globally. So in 2019, it was a particularly hot year in some places, China, South Asia, many parts of Africa, some parts of Europe, not so much in the United States, but Central America, South America, and in Australia, they had a particularly hot, horrible year where they were seeing temperatures in excess of 40 quite regularly, and it was it was unusual for them to see that. So it does vary. It's not consistent throughout the entire world. So another indicator of that is kind of the North Pole sea ice, because since it's not on land, it doesn't stay frozen. But if you watch the chart, it starts at about a volume of 25,000 cubic kilometers, and then by 2017, it's dropped to only 15,000 cubic kilometers. So we've lost quite a bit of sea ice in that time. Excuse me. And we are also seeing temperature anomalies. I mentioned Australia, they're in the center, very extreme temperatures hitting there, causing wildfires, very dry conditions already there. On the left, you see the far north and North America, and even parts of Asia, Europe there with northern parts of Russia and Scandinavia hitting record temperatures, so that in January it was above freezing at the North Pole, which is just not, it does not happen. In the US, we've had unusual, where we've had temperature excursions of 10 degrees, 15, even 20 degrees above normal in what normally would be our cold time of year, January. If we look at taking that data, same sort of data, again, the global average temperature through 2020 is already looking at above 1.2 degrees. And you see the last 5 years are still the hottest on record, and that's continuing. So 2020, again, you see kind of warm spots, hot spots there. And 2021, we have not consistent. India particularly had a cooler year, and there are parts of Central Asia as well, and Antarctica. But in general, globally, the Northern Hemisphere was quite warm this past year. There's a great resource, berkeley-earth.lbl.gov, that you see there at the bottom. And so I pulled up what it shows for Istanbul, and be able to extrapolate back based on the data they have back to 1758. So we have 260 years of data to be able to show what's going on there. And you'll see some temperatures, early 1800s, the mean temperature was a little higher, and then it dropped back and consistently. But if you look from about 1840 to 2000 or so, we have a trend that it's getting progressively warmer. And then suddenly, just about 2000, that change has gotten some more significant. So the mean temperature for Istanbul, instead of being around 13.5, is now up over 15, and that is increasing. And you see that kind of in the ribbon bar at the bottom, which just shows a snapshot for each year for the last 150 years of what's going on, and you see the average temperatures there are progressing from the blues to the reds. So we are definitely seeing that trend already. The other thing to look at is what are the coldest and hottest months, and you'll see in the past 15 years, only 3 months have actually made it into the top 10 of being cold months, setting records for that particular temperature or that range. If we add the hottest months, almost all of the records and most of the temperatures in the last few years have all been set in the last 10 years or so. And if you go to the annual column, you'll see that 2018, 2017, 2020, 2019, 2014, and Istanbul were the 5 hottest months. Sorry. If you look at the high temperature too, you'll see that we're seeing kind of a range in extremes as well. That the uncertainty gets better as we get to about 120 years ago. Then but if you look back about 2000, the average max temperature in Istanbul was about 18.5, and now it's moved up to 19.5 in just 20 years. Similarly, we're seeing low temperatures also increasing, so that at 2000 we're looking at 9.5, and then we're approaching 10.5 at this point. So we're seeing a shift to both the high and the low temperatures here, which is consistent with what the models show. So there's a great book if you're interested in building performance simulation that has many topics, 22 chapters working on different aspects of that. But one of the chapters specifically is weather and climate, and how do you deal with that? So my next part of the talk is going to be derived from that, and I'll show you some of the information. So what we talk about in that chapter are applications for simulation. And then what are their needs for climatic data and how they deal with it. So if I'm looking at doing energy evaluation, energy design, maybe compliance analysis with standards, I need a full year of data. Typically hourly is about the best we can expect. So if I'm looking at other things, maybe equipment sizing, third column, third row, design day or short period calculations, where you're using near extreme conditions to size your equipment. If you're trying to calibrate a model to existing building energy use, you might need weather data during the period that's collected near the building site. And other things, you may natural ventilation design, you're going to need local wind, and that's one of the very difficult ones. The sources for much of our data is still from airports. There are new sources available, but needing locally measured data is pretty important today. Another one, daylighting studies. Hourly luminance is just not sufficient. If you remember back to my chart about the variability, well, illuminance is one of those things that changes quite radically, even within a few minutes, due to moving clouds and different conditions there. So you may need that sort of information in detail. Similarly, what are the elements you need? And so these, I'm not going to go through everything here, but dry bulb, that's one of the easy ones because we record that in many places, not just airports, and being able to get that. Similarly with humidity, solar radiance, a little more difficult to get. Till recently, that was mostly calculated just because of the very few places were actually recording it. One of the interesting things that's happened recently is that a number of the data sets have been merged together in what's called a reanalysis data set. So a single data set from satellite data is now able to combine many things from this, and they are particularly good at solar. Excuse me. So cloud covers, mostly we need that for daylighting sky models. Wind velocity and direction, interestingly, that's one of the things that can be derived from these reanalysis data sets, is they can sense velocity and direction of wind from the satellite data. And then other things you'll need there. Wind is one of those things that's notoriously missing for many cases, and depending on what you need, particularly, it may be important to try to find good sources. The higher in this chart you go, the easier it is to get data. So climate data, when I started my career, was scarce, and there were just a few what we call weather tapes, because they were physical magnetic tapes back then, available. Then that was what we had to use. Data was only available from ground observing stations. Rarely do we see solar data. Good range of other meteorological aspects. The wind data is problematic. At the airport, it's usually an open space, no obstructions, and if we're talking about a city or we've got any sort of terrain variation, it'll make a big difference. And other data is often limited or just not available. Now, I mentioned the satellite data. The accuracy is quite good. They've been working with NASA here in the US on some of their data, and they are able to replicate some of the design conditions that are in the ASHRAE handbook within about 1/2 degree, which is pretty remarkable given that it's gridded data and that it is remote. It is not a temperature on the ground. The good thing about it is we have a globally consistent data set, a relatively decent grid that's getting better. Some of the data sets, there's the ERA5 in Europe is dropping down to a 30-kilometer grid, so it's actually quite fine resolution for that. There is some issues with these data sets. They tend to not do well around large bodies of water, so coastal data is not as good as inland data, but to have a consistent data set, they're actually quite good. So there are global master data sets. The US NOAA, the National Centers for Environmental Information, are a repository for data for the World Meteorological Organization, and these data are updated nearly real time. You'll get them usually at least the next day, and it's pretty accurate. They keep that data set and keep expanding it. But the data we use as engineers and doing building simulation is that we need more, I guess, summary and calculation. For design conditions, we've got to do that, derive that from the data of some historical period, and we need other data that maybe the ground stations are not recording, particularly the solar radiation, because the global data sets that WMO hosts are not real time, or do not include solar data for the most part. So when I'm talking about design conditions, these are the temperatures and humidities, maybe even wind conditions that you're using to size the heating, ventilating, air conditioning maybe dehumidification equipment. They're also used in other industries, agriculture, industrial applications as well, just trying to get a feel for what they are. Within the ASHRAE community, and what's been typically used includes dry bulb, wet bulb, and dew point, and maybe wind speed, with various frequencies of occurrence for those. In the US, we typically use a typical percentile of 99.6 for heating and 1% for cooling. Now, what that means, the percentiles are representative of the number of hours that you might expect the temperatures will be exceeded in a particular year. So 99.6 means we've got 0.4 hours, or about 35 hours a year that it's going to be colder than that. For the 1% case, that means we're going to see about 88 hours a year that are going to be warmer than that particular case. And that's partly just to, we don't want to design for the most extreme condition because it won't reach that very often. So there's kind of a balance of reasonableness and being able to meet the load, at the same time not paying for more capacity than we need most of the time. So different applications, they're different percentiles, and ASHRAE now is recommending using monthly cooling calculations, often because the peak loads may not be in the middle of summer, particularly as sun angles drop. We'll get more direct sun on surfaces and windows. Later in the summer, such as August, September, even October, we've seen variation there. So chapter 14 of the ASHRAE Fundamentals is the most comprehensive source I'm aware of. They have over 9,000 locations throughout the world. That's up about 1,000 over the previous handbook. It does get updated every 4 years. It uses much of the data comes from that WMO repository at the NCEI, and includes data through 2019. So this begins to give us a snapshot of what's happened in that past hottest period there, where 2016 on are the hottest years, and we're beginning to see some of that in there. In a study done earlier, this would have been for the 2008 handbook, the location, they were looking at locations that had existed in the period of record for a long time, and what they were already seeing that that design condition was changing in that case, and we're seeing an increase in the dry bulb temperature of about 1.5 degrees and the cooling temperature about 0.8 degrees. So we're already seeing that in there, and kind of see that in some of this. Some of these, some of the stations are don't have a real strong signal or no signal, and you see it varies from some of the locations actually got a little cooler, some of them got quite a bit cooler. And so the changes are still relatively small in the range of 0.05 degrees per year, but we are seeing that change specifically in the signal. So the handbook, these are where the 9,000 locations are. You see fantastic coverage in North America and Europe, and pretty much through East Asia. Excuse me. But Africa is kind of problematic. South America, well, a lot of that is still the Amazon, so there's not a lot of locations, but where the population centers in South America are actually pretty decently covered. The one thing that was kind of disturbing about this, you see South Africa having lots of locations, but the largest economy in Africa, which is Nigeria, they're kind of in the corner of Africa, had no locations until this year. There just wasn't sufficient data to be able to drive that. ASHRAE provides an online station finder so that you can go and translate that data. You see the numbers here, and what those represent are the number of nearby stations for that. So I can zoom in on this. I zoom to Turkey. I can begin to see that there's good coverage in Turkey, not complete, but there are coverage. Everywhere you see a darker circle with a plus in it means that there is a location. So I'm going to zoom in to Istanbul and try to look at there. So we have, you can see that there are a number of the old airport, the Ataturk airport there south of Istanbul, and then a number of others throughout the area. So let's zoom in a little further. We can see the airport there. And then if I click on that, what I will get is the single page summary. And this is gives all the data we've been talking about, and I'll go into more detail, but we've got annual heating and cooling, we've got monthly design condition, and we have historical trends as some of the key features here. But you'll begin to see a lot of the different parts of that and how that works. So if we zoom into the top, this is where the annual heating and cooling design conditions are. So for heating, dry bulb at 99.6, we were just talking about, it's set at -1.4. If we do for annual cooling, if we're looking at the 1.6 or the 1 degree, sorry, we're looking at a dry bulb of about 30.9 and so on. You can see the variation there going on. There's also a section on extreme annual conditions, and these include wind speed, and then there's some derivation of what it might be based on statistics, not based on data of the wet bulb and dry bulb. The max temperature might be as high as 39, min temperature -10, and that's based on statistics, not the data. The next section is monthly, and that includes temperatures, degree days, degree hours. Also wind speed by month, so you'll see annual variation on that. Precipitation also, and then followed by those same design dry bulb and wet bulb temperatures. So you can see that based on annual and by monthly basis, you can see how they vary over the year. Main daily temperature range, and then finally on to the bottom, which is also includes a clear sky, solar radiance for design calculations, as well as an all sky. Something new that got added this last time is the historical trends, and what you'll see there, where there is a statistically significant trend, we'll begin to see. So the station already is showing about a ½ degree change, 0.59 degree in the 1% dry bulb, and changes we are seeing in the degree days as well. So that's not unusual. There's also regional variation and seeing similar, but not quite as strong a cooling increase temperature there. I mentioned NASA Power. This is the NASA website. They're able to replicate the same sort of information. They have not done a complete set. There are some pieces missing. You see the gray there, but they are actually able to replicate the same point. You can select the time extent, so you can match the data set there, and that is continuing. The data is continuing to get updated. Unfortunately, the solar data is not updated, has not been updated since last year. So it's not quite up to date on that, but all the temperature and other data are, and it's quite a useful resource. You can also get hourly data out of here, which is kind of one of the key things here. So if we're looking at climatic data and building simulation, we need data usually from a single year. We're not doing multiple year. You can do multiple year, but usually we're looking at kind of a snapshot there. The typical or meteorological year, or TMY, is kind of the most widely used. There's an ISO standard around that on there. Essentially, it's a composite of months. They won't all be from the same year. Each is representative of that period that you're studying for that. So the months are selected kind of using statistical indices around dry bulb, dew point, wind speed, total. And each of the methods kind of has a little bit different weighting. So maybe temperature and humidity may be weighted higher than solar radiation in some cases, or other way around. So they will, you can find which ones work best for that. And there have been various studies, and they do make some difference, but in general, they often give same sort of results. Sorry. So the typical, the TMY data sets are really best for certain things. If you're trying to look at alternatives during design, say I want to compare two different windows, maybe a low E to a double pane, and so they're going to give me, they're keeping the climate data the same. I can see what the variation there due to that, or maybe an increase in insulation or an efficiency on the HVAC. They also are ideal and are required for most where you're looking at trying to do a performance method for building standards or codes, and even the green building rating system points. They want you to use a consistent data set. Some of the limitations, though, they're not representative necessarily of extreme conditions. Remember, they're trying to be typical. That doesn't mean they won't have some extremes in them, but they also may not represent design conditions. I see that they mostly can be, but I haven't seen some of the older data sets. They were very different from the design conditions. Now they're not close, but they can be mild. So there are lots of data sets available out there. There you see all sorts of ones here that are available and kind of throughout the world. I know there's one available in Turkey as well. It's not necessarily on this list. I'll talk a little bit more about the one on the bottom, the TMYX, as we get toward the end, but that's the most comprehensive with a global data set of 13,000 stations at this point. Actual weather data is also needed. Sometimes you need that if you're going to try to calibrate an energy model to a utility bill. You need weather data matching that period so that you're not trying to do that. And that's become increasingly useful and available. There are many sources out there. Some of them, I mentioned the WMO data center at NOAA. That data is available, but again, it has no solar data. And then there are a number of other private and public sources. Many of the national meteorological offices will also can provide that data similar to what NOAA does, and they often will have more data. NOAA's data set includes about 20,000 stations globally, but that's what's reported by each country, and they don't always report everything. So biggest issue in working with any of these data sets is how complete are they? Does it have what we need? Have at least temperature, humidity, wind, and solar? And the answer is often, but not always. Some of these are really more focused on kind of the snapshots of what you're looking. So if you're looking at some of the public sources, temperature, humidity, and wind is about all you're going to see, and you're going to have to fill in the solar radiation data for you to be able to use these. This only is through 2016, but this is the longest contiguous hourly data set that I can find globally. There are a number in Europe that have significant gaps in the 1940s after World War II, but this is actually an airport near me here in Washington, D.C. Starts in 1938, and we have contiguous data through today. And so it's a variation. So what I've done here is taken a medium office building about 3,000 square meters and simulated it using the actual data and showing the variation. Now the top parts don't really vary because those are scheduled, but if you look down the red and the orange and the blue and the green, those are what's varying, and you can see quite a bit of variation there, plus or minus 10%, sometimes 20%. depending. And it doesn't, there's no one indicator that could tell me which is going to be best for that. It could be, because for example, you could look at 2012 and it's lower, but it's lower primarily because it was a particularly mild winter. So, and the summer wasn't quite as hot. So it's not just heating or cooling, it's a combination of the two. The good news is if I draw a line through them at where the TMY for that is, then what I'm seeing is the TMY does what it's supposed to do. It's capturing kind of the median of what's happening. It's not as extreme as some of the years, but it's also not as low as some of the years. And that's what the usefulness is. But if you're trying to capture some of this variation, you would need actual data. So what's happening? The past 5 years have been the warmest on record, as we've already talked about. The fundamentals, just because in the ASHRAE handbook, are updated only every 4 years, it can quickly lag. And the difference between the 2017 and the 2021 handbook was quite significant because we were capturing those 5 years that had already changed. The TMY data sets are also infrequently updated. The one in the handbook, or not the handbook, but the one that's typically used in the US, the TMY3, just partly because it was easily available, has data through 2005. So it has not caught any of the last 16 years of more extreme data. So we did a quick look at 12 locations, see, doesn't matter. Are we seeing something that changed there? So this is a list of some of the data sets we use, some of the earliest ones in the US, TRY, TMY, and then through TMY2 and 3, IWIC, which was an international set from ASHRAE, and then IWIC 2. But those only go through 2008, and then the more recent TMYX that I mentioned. So we began looking at the typical data sets and seeing what's going on there. And I've got a range of climates. So from a heating standpoint, if you look to the right, Singapore, Sao Paulo, or very little heating. New Delhi, LA, kind of same sort of thing. But if you look at the lines, they're all decreasing, meaning it's getting warmer. And that's pretty consistent throughout all the locations there. If we look at from a cooling standpoint, we get the opposite sort of impact. The bottom right where you see Resolute, Resolute's a very high latitude location in northern Canada. It's above the Arctic Circle, so it has essentially zero cooling. But if you look at all the other locations, we're seeing a trend, not always up throughout the data sets, but consistently by the end, we are seeing increases. All locations, even some of the hotter locations are continuing to get hotter. So Cairo, Delhi, Singapore, all in that area. But even some of the milder locations like Los Angeles and Washington near me also are changing. And then if we go and look at the design conditions, these are the heating design conditions. So starting from the oldest to the newest, how they've changed. And so if we start at the top, Buenos Aires has increased about a degree or so, Cairo about 1.5 degrees, London Gatwick and Heathrow very similar, Los Angeles, Resolute also, although some of the early temperatures were a little cooler, it's now moving that direction. And this is a snapshot of the handbooks across the past 24 years, the past 6 handbooks. So we are seeing changes consistently through there. Delhi is one of the cases that it is going a little lower, not quite sure why, but that's one of the few that did not go in that direction. If we look at the cooling design changes, you see consistently all throughout, except for Winnipeg down at the bottom, where it's getting slightly cooler, not quite as warm. The design conditions went from about 28 to 27.5. But every other case, you're seeing that the latest bar is further out than some of the earlier ones, and distinctly so that you see that jump change that we've seen partly because of the temperature differences. If we look at what that converts to in terms of energy use and how that impacts, what you'll see is a consistent change for locations that are cooling dominated, and think Delhi, Sao Paulo, Singapore, and some other locations. What we're seeing is a trend to higher energy use. For locations that have significant heating aspects, kind of a mixed bag. So in Washington Dulles, if you look to the right, the second to the right bar, actually seeing a decrease in energy use. But if you look at the red that represents the heating, it's going down, and that's pretty consistent even with what we would expect from the changes due to the temperature. So we are seeing changes. It's not consistent across the board, primarily depending on what's going on in terms of heating and cooling swapping for that. If you just separate out the heating and cooling, you can see that more distinctly. So in Cairo, the second set of bars there, you see cooling increase and heating decrease consistently there. So that's a kind of a change. But if you look at, say, for example, New Delhi, heating is almost non-existent, but cooling is significantly increasing, and seeing that in many of the other locations as well. One of the other things that happens is that our data is kind of sparse. This is an aerial photo of Washington, D.C. area. And toward the center, there's a push pin just below the where it says Washington. That's actually the national airport that I just showed you earlier. If you go to the far left, you'll see Dulles Airport. That's also one of our airports. And then just to the right of the national airport, that's Joint Base Andrews. That's where Air Force One lives. There was a study done in 2018. They went and did a measurement of the city and see what the temperatures around various parts of Washington particularly were, and did an overlay. And if you look just above the name Washington, you'll see a kind of a forested area. That's actually a national park that's in the city of Washington for that. But watch what happens when we overlay what the temperatures were. And now these temperatures are recorded in Fahrenheit, but what we're seeing is a variation of about 7 to 8 degrees from hottest to coldest, so that the built up areas of the city are very much much hotter, so that we can see temperatures that are 10, 15 degrees, maybe even 20 degrees warmer. So that park, the Rock Creek Park there that I mentioned, the national park, is cooler significantly on even one of the hottest days of the year. This was in August, and that's definitely our period. Also, the water, the river that flows through there, you see kind of to the top left, that's having a cooling effect as well. So all this plays into play. And you remember, the airport is right there, kind of off the center. It's very much affected by the water and the temperatures there. So urban heat islands are a huge influence on what we should be doing.
Drew, we want to also spare some time for the questions. So
yes, I'm close.
Yeah, okay, thanks.
I'm gonna move quickly through this. There are a number of methods for creating future climatic data. I'm going to really focus on the third one, the serious time adjustments. That's what's been used more regularly. It's just basically shifting and stretching. The two above are very computer intensive and physics based or statistics based. So there's also an analog, and I'm going to show you just quickly what analog would be. There are sites, at least for the US, that shows you what the future temperature would be like, and so you could look there. I did one recently up in Michigan, and the location was relatively mild, but it's going to get significantly hotter, and that's what you can do with analog, is find a climate that is similar to what is predicted that you'll be in the future. So the IPCC, and this is showing the 2013 new data has just come out just this past week. You've probably seen some of it, but the data is what's there. They develop storylines to represent different pathways forward, sociological, technological, and environmental for that. And they're each updated for each report. As I said, the AR6 assessment report 6 is just was released just this, I guess, on Monday. So I don't have that. So they have emission scenarios, which they call RCPs, or representative concentration pathways, and then they represent the range of potential climate impact. So that's when you see charts like that, that's what you're seeing is kind of the range of what each of those are predicting over the period. So if we take the data and using that third technique, morphing and the stretching, what we're going to see there are temperature changes, both monthly, diurnal, and then some cloud cover to be able to recalculate solar radiation and also precipitation. And so here's an example of one done. This is Los Angeles on a typical fall day, and the yellow is the existing drive bulb temperature, and then there are 4 lines for the RCPs representing what could be in the future. We've got a temperature base day to nighttime range, also the diurnal, which tends to be a little bit less for each of the scenarios. The nighttime temperatures tend to remain higher, but there also is a change in the temperature between that base and the scenario. For Heat Island, it's similar, but it seems to be roughly a function of population beyond about 5 million people. The extreme seems to be around 5. Now that's an annual average. It varies quite a bit day to day. You saw the temperature variation there in Washington. Just a bit about it depresses the daytime temperature and raises nighttime temperatures. So this very similar, but I'm just gonna click through it so we have a little bit of time here. This shows Washington Dulles, which was one of the sites that I showed you on the Heat Island. And what we've got is the TMY, the typical year, versus the 4 scenarios. And what you're seeing there is on a seasonal basis, yes, cooling is getting higher, but we're also seeing cooling getting pushed out into the other parts of the season. Site energy tends to decrease in this location. That's consistent with what we saw. Heating's lower, source energy's higher, but low energy buildings tend to mitigate most of the impact is what we're seeing. In Singapore, it's kind of the opposite. There's no heating, so we're just seeing an increase in cooling. And again, low energy buildings are kind of mitigate that, even in the semi-tropical, tropical. For Toronto, kind of an inland area where heating is still pretty dominant, we're seeing a decrease overall, but a significant increase in cooling, meaning that a lot of that cooling equipment is going to operate twice as often, maybe twice as long as it did in the past. Similar sorts of impact on the source energy side, and Toronto again. On Heat Island, similar sorts of impact, not quite as distinct as there, but we're getting combination of Heat Island along with the other case as well. On a monthly predicted change, we've got kind of similar sorts of things, but now we're seeing in Toronto again that push into other parts of the year that normally would not have cooling and significantly less heating. The northern climate's even worse, but we're seeing 40% change in heating there. Keep moving here. The largest changes we are seeing really is in the monthly end uses. So you kind of see a snapshot here. We've got Cairo there where there is significant heating, or it can be cool for a few months of the year, but now we're seeing significantly hotter summers and winters as well. Sao Paulo, Brazil, where they really don't heat, but there are many months that could be heated. Now it's just primarily cooling dominated. You've seen Dulles there on the bottom left, but then Singapore very similar. Just all the months are getting even warmer. So I'm gonna skip through this so that we've got time and leave it at there. So, okay, Gülsu, I'm ready.
Okay, thank you,
Sorry.
Drew. Thank you. It's really nice information, nice statistical data regarding to weathers. Thank you. And I'm sorry that here the electricity was cut off, and I am now have a candlelight, in a very romantic atmosphere. Sorry for that. Anyhow, there are questions actually. I just quickly ask those to you. One is related with directly an advice, asking an advice from you, that it is considering the climate change scenarios, the RCPs. What kind of recently, which one of the simulation programs, tools can be used? Actually, for instance, Design Builder is have a good interface for that. Is it possible to use this tool or any other tools that you advise for the designers, for the professionals?
Right. Sure. I think any of the tools such as Design Builder can handle the variation to look at this, and they're, as long as they can either accept adjusted weather, and there are many sources. I didn't go into that, but there are a number of sources where you can purchase data. There's some free tools out there where you can get adjusted data for representing future climate, and so I think just about any tool that is flexible in using a variety of weather can handle that.
Yep. Actually, one related question is related with the simulation weather files that reflect future climate change scenarios, or any tools that can be used to modify TMV files to reflect IPCCs or other climate scenarios.
Right.
Do you advise or recommend any good sources for that?
Most of the sources I'm aware of are for fee, and I haven't spent a lot of time looking at them in general. Many of them use the morphing method that I was showing, where they're stretching and kind of readjusting existing weather data, the TMYs to future. I've not spent a lot of time for that. There is an older tool out of the University of Southampton that can do that same sort of thing, but it only deals with one scenario, and it's not the most recent scenario. So unfortunately, I don't have any one to recommend at this point.
Okay, actually, one question is regarding to the TMV data as typical meteorological year data, averages data from various years. How does it deal with temperature change due to global warming in recent years or decades? Similarly, does it make sense or required to make extrapolations of temperature change to account for global warming effects?
Often I don't worry about it. This is the TMYX data set that I mentioned earlier, and you can see there are 80 to 100 locations in Turkey there, and this includes data through 2018 at this point. The data set does have, we're working right now on an update to include through 2021. When people ask if we should do simulations and include data through future data, I ask how long the equipment and the building and the systems are going to last. And generally, our equipment lasts 10, 20, maybe 30 years. And so by that time, we will have new data to do our design conditions for. Also, many of the design calculation methods have so much extra capacity built in, 10, 20, 30% oversized, that you will probably never see anything reaching that during the life of that equipment, or maybe even over the next 80 years or so. So we're not seeing, we're talking about a degree and a half, or maybe even 4 for worse conditions. And so that's just not something that equipment will ever have to deal with regularly.
Yeah. Okay. So thank you. One other question is related with the pandemic effect, actually. What is your opinion about that? How the pandemic affect the climate change? Is there any differences on projections regarding to that?
I'm sorry,
Yeah, this is directly related. Is there a relation, actually? First, maybe this question will be better. These pandemic effect and climate change. I mean that these pandemic effects that all the world in now last 2 years will change also something in the projection of the climate change, or the other projections regarding to the also the people inside of the buildings and the building's performance. What do you think about that? How pandemic will change the projections, or does
Yes.
it change?
Yeah, I actually left out a slide there to show what had happened in the pandemic, because our commercial buildings, our office buildings, energy use went down pretty significantly in 2020. It's already rebounding. I know that here in the U.S., many companies are already beginning to require people to come back to the office, and many of the commercial sectors, other commercial sectors that were so down, are now back. And what it looks like is we're seeing kind of a rebound back to 2019 levels of energy use. So I think I'm not an expert in this area by any means, but what I hear is that increasing temperatures can make diseases worse, particularly spreading. But fortunately, if it's warmer, we can spend more time outside. So there's kind of the advantage that we can do that as well.
Okay. Okay, Drew, thank you so much for this nice presentation. We really this really comprehend information for us regarding to the climate change and how we can deal with the weather data while we are using building simulation. So thank you so much for sparing time for us. Hope to see you one day, the good days in the future in Turkey. And we just close our session now. Thank you for the audiences, their nice questions, and to listen us. Okay.
Thank
See you
you.
then for the.
All right.
Thank you. Bye-bye.
PP bazlı 3 katmanlı yapısıyla ses yalıtımlı, yangına dayanıklı, üstelik halojen içermez. GF Hakan Plastik'ten GF Silent Extreme sessiz koruyucunuz.